In 10.2 A, B, and C, we're going to describe the characteristics of a sampling distribution of x bar 1 minus x bar 2. We'll talk about how to calculate probabilities, and then we'll also determine whether conditions are met, computing the differences in two different means. I'm actually going to have us skip this activity about polyester and decay. I will tell you this section works very much like section 10.1 did, except we're looking at quantitative data and not categorical data. So let's dive into the process. If you are dealing with a sampling distribution of the difference between two means, again, we're going to refer back to Chapter 6 and Chapter 7. Remember to find the sampling distribution of the means, and if we had to find the actual mu or mean of it, we use the actual mu. So how do you find the mu of the difference of distribution 1 and distribution 2? You just subtract the two means, just like before. Well, how do you find the standard deviation? When you combine two random variables, remember, even if you find the difference of those or the sum of two random variables, the standard deviation is always combined or added. Do recall the initial standard deviation was actually the standard deviation over the square root of n. So what you have to do to combine two standard deviations is you must convert the standard deviation back to a variance. To get that to its variance, remember you'd have to come in and square it. So when you square this, what you're going to get is sigma squared over just the regular n. That square root's no longer there. You're going to do this for the first sample and add to it the variance of the second sample. Once the two variances are combined, take the square root, and now you have the standard deviation of the difference of the sampling proportion of the means from two different samples. That therefore is going to be your new normal distribution. Just like before, we must check the three conditions of random, independence, and normalcy. Random is just what we're looking for, again, our random sampling or an experiment. For normalcy, we do have to check both sides of it for the means, so we're hoping it meets the central limit theorem for both sample 1 and sample 2. If not, by the way, if it's less than 30, you're going to have to graph it out because remember, the T procedures are not robust, and you're going to look for little skewness and no outliers. We're then going to wrap up with our independence test, which is the population greater than or equal to 10 times the sample size for both of the two samples. So let's look at this potato chip example. A potato chip manufacturer buys potatoes from two different suppliers, Riderwood Farms and Camberley Inc. The weight of the potatoes from Riderwood is approximately normal, with the mean of 175 and standard deviation of 25 grams. The weight at Camberley is approximately normal again. The mean weight is 180, standard deviation of 30. When shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each of the samples and weigh them. They're surprised when the average weight of the potatoes in the sample from Riverwood was higher than that from Camberley. Let's describe the shape, center, and spread of the sampling distribution. Now, the nice thing, the two samples are already coming from approximately normal populations. Therefore, for the shape of the sampling distribution, I'm going to call it x bar C, which is from Camberley, minus x bar R, which is from the Riverwood, is normally distributed since the population distributions are approximately normal. Now the center, define the difference. Be careful, we decided to actually do Camberley minus Riverwood. So for the mean, I'm going to take 180 minus 175. Which just gives us then our center at 5 grams. Now for the spread, be careful. We are going to have to go on in then. I'm going to take the standard deviation and I'm going to square that over the sample size, add to it this other standard deviation squared over the sample size. Take the square root of those combined variances to get the new standard deviation of this. So we now have the description, our shape, center, and spread of our new distribution, which is the difference of the two means. Using that, let's do a probability question. Find the probability that the mean weight of the Riverwood sample is larger than the mean weight of Camberley, and should the inspectors have been surprised. So I have to be careful on how I define my variables first of all. Remember, the mean of Riverwood of the sample is larger. So it has to actually be negative. So what we did is, recall, we came up with the mean of 5, but we did Camberley minus Riverwood. So the difference was 5, but I actually want it to be negative because if Riverwood is larger this calculation would have been negative. So what we want to find is that the probability of Camberley less the Riverwood is less than 0. Again, because this problem says what's the probability Riverwood is larger. So we can compute the z-score. Remember, back when we did z-scores, it was our piece of data or the mean minus the mu over sigma. So we're going to do the same thing for our z-score, but it's a combined variable. So down here what we have is we see for x bar c minus x bar r, remember we want to find when it's less than 0. So as it stands, this is at 0. So that's why I have 0 minus the mean difference of the two, which we found earlier was 5, over the standard deviation. If we look at the graph of that, what you're going to see is, remember, the mean difference is here at the middle of 5. We want to find the probability that the mean difference is less than 0. Well, 0 is somewhere in here. I'm just kind of estimating it's right about there. And I want less than, so I want the area to the left. Now, there's two ways you can actually calculate this. You can do normal CDF with the standardized data, or you can just keep the raw data. The standardized data, by the way, when we compute the z-score here, it's negative 0.57. So if I do standardized, this is a 0.57 standard deviation to the left. So I'm going to do negative 999 to negative 0.57 of 0 and 1. Now if I keep just the raw data that we had before for the mean and standard deviation, what I want this time, this is another way to look at the curve, is I actually want to have it from negative 999 to 0 as my weight. But the mean of my distribution was this, and this was my current standard deviation. If you do that, what you're going to end up getting is that the probability is 0.28 with either of those formulas. So, should they be surprised? Well, ultimately what you could say, the inspector shouldn't be surprised since the Riverwood sample would have a higher mean over 1/4 of the time. This probability is definitely somewhat likely to happen. So it is not surprising that Riverwood has a larger weight than that of Camberley. I will tell you, ultimately, I think this is probably one of the trickier types of probability questions to have to address. So just be thoughtful. If your brain first goes to about standardized data with z-scores, that's great. If not, I do recommend, and I think it's easier, just to always do normal CDF, but find your current mean and standard deviation of your new distribution like we did here with the 5 and 8.75, and then just think about what they're asking you for lower bound and upper bound. It tends to be an easier approach to this type of problem.